So in the last lecture, we have seen how to find out the velocity of sound in the gaseous medium. Okay, means we derived the formula for determining the velocity of sound in the gaseous medium, and that formula is V is equal to root of K by rho, where K is the bulk constant of the gaseous medium and rho is the density of the gaseous medium. Now we will see that how Newton has used this particular formula and applied his own theory to determine the velocity of sound in the gases. Okay, so now we come to the experimentation purpose. So there is a Newton's formula for calculation of velocity of sound in air. So what actually Newton assumed? You see, we are considering the gaseous medium, that is the air medium which is surrounding us. Okay, and we are thinking that whatever sound wave is propagated, that is propagated in the gaseous medium, and we want to calculate the velocity of the sound waves in the gaseous medium. Now what Newton assumed that whenever the sound wave propagates in the gaseous medium, the whole of the process is isothermal process. Okay, because whenever the sound wave will propagate through the gaseous medium, the sound wave propagates in the form of alternate compression and rarefaction. So there will be the increase in the density at certain points, and there will be the decrease in the density at the other points of the air molecules. Okay, so there will be the compression, rarefaction. So this particular phenomena, Newton assumed that this particular phenomena is an isothermal process. Now whenever we say that some process is an isothermal process, it means that the temperature of that particular system remains constant. So temperature remains constant, therefore for a given mass of a gas at a pressure P and the volume V, suppose P is the pressure and V is the volume, we can write for isothermal process as PV is equal to constant. So from thermodynamics itself you learn that PV is equal to constant. So let us differentiate this equation. So P and V, these are the product of two functions. So let us keep first function as constant and differentiation of second, that is dV, plus second function as constant and differential of first function as dP, and differential of constant will be equal to 0. Therefore P is equal to this V into dP, that will be in the right hand side. Okay, and this dV will be in the denominator, and this can again be written as P is equal to minus dP upon dV by V. Okay, I am taking this V which was in the numerator in the extreme denominator, so that after solving it will come into the numerator only. Okay, so this particular equation can be written like this. Now what is dP? dP is nothing but the change in pressure. Okay, whenever we differentiate some function, we are actually finding out the change in that particular function. So dP is the change in the pressure, dV is the change in volume, divided by V is the original volume. Therefore change in volume divided by original volume, this is nothing but the volume strain. Okay, so this is the strain. Change in pressure is nothing but stress. Pressure is nothing but force applied per unit area, and force applied per unit area is nothing but the stress. So stress divided by strain. So this will be the volume stress divided by volume strain, and it is equal to the bulk modulus. Okay, and that is nothing but the K. This we can write with the help of Hooke's law. Okay, so here we have found out P is equal to K. Earlier we have noted that in the formulation for the velocity of sound in air, that formulation was V is equal to under root of K by rho, and we earlier itself we told that it is very difficult to determine the value of K. Okay, so we have found out indirect method. Instead of determining the value of K, we will determine the value of P, because P is equal to K for this air gas medium, right? So our formula now becomes V is equal to under root of K by rho, and that will become now P by rho. Now pressure, it is very known quantity. What is the pressure of the gaseous medium? This is very known quantity. So at 0 degree Celsius, this pressure is equal to 76 mm of Hg. So 76 multiplied by 13.6 into 980 dynes per centimeter square, and rho, that is the density of the air at 0 degree Celsius. So that will be equal to 0.00129 gram per cc or gram per centimeter cube. So if you put all these values, we will get V equal to 280, that is 280 meter per second. Okay, but we know that the value of air in the gaseous medium, so the value of sound in the gaseous medium is 332 meter per second at 0 degree Celsius. So therefore whatever value we obtained by using Newton's formula, this value is not correct. Okay, so Newton was not succeeded in determining the accurate value of this velocity of sound in the air. Okay, hence Newton's formula must be corrected. It is not acceptable. So what next then? Who determined the value of sound in the air medium? Then there comes Laplace. Okay, Laplace is the name of scientist. So we know that earlier while observing the Newton's formula, Newton has assumed that whenever sound wave propagates through a medium, it forms compression and rarefactions in the medium, but the whole process can be thought of as an isothermal process. Okay, so Laplace came forward and he told that no, the given process cannot be isothermal process, since there is a formation of alternate compression and rarefaction, and this formation is quite rapid. Okay, this formation is quite rapid, and therefore whenever there is a formation of compression and rarefaction, temperature must not remain constant. How the temperature can remain constant there? So Laplace argued that temperature will not remain constant, and if the temperature of the system is not remaining constant, such a process cannot be called as an isothermal process. Rather, such a process is called as an adiabatic process. Okay, so Laplace assumptions were based on these three assumptions. Okay, number one is that compression and rarefaction in the sound waves takes place very rapidly. Why the temperature doesn't remain constant? Because whatever compression and rarefactions are there, this takes place very rapidly. Distance between the compression and rarefaction is large. Okay, because the wavelength of the sound wave is very large, across 1 meter, 2 meters, like that. So the distance between the compression and rarefaction is also very large. So there cannot be a rapid exchange of the temperature between the compression and the rarefaction. Okay, it will take some time. Again, if the temperature has to remain constant, there must be the flow of temperature from one point to the another point. Okay, or there must be the sharing of energy from one point to the another point. However, whatever air molecules we are thinking of, these air molecules are very poorly conductor of heat. So heat cannot propagate from one point to the another point, so that temperature should remain constant. So temperature will not remain constant here because the air is very poorly conductor of heat. Okay, so based on these assumptions, Laplace argued that no, the process is not isothermal. The process is adiabatic actually, and if the process is adiabatic, instead of writing PV is equal to constant, we have to write PV gamma. PV raised to power gamma is equal to constant, where gamma is called as the ratio of the specific heats, Cp by Cv. Gamma is equal to Cp by Cv. So that you have already studied in the thermodynamics, right? So now differentiate this particular equation. So first function into differentiation of second. So differentiation of second will be gamma into V gamma raised to power gamma into V raised to power gamma minus 1, and into differential of V, that is dV, plus second function, that is V raised to power gamma, into differential of first, that is dP, and differential of constant will be equal to 0. So if you arrange these equations, finally what we will get? We will be getting P into gamma, and it is equal to minus dP upon dV by V, which is nothing but stress divided by strain, and it is equal to the bulk modulus K. So Laplace found that the value of K should be replaced by P into gamma instead of P only. Okay, so velocity of sound in air, it will be equal to under root of P into gamma divided by rho. Okay, and the value of gamma is also well known, that is the ratio of the specific heats for constant pressure and constant volume. So it will be equal to 1.41. This is the constant. Okay, it can be derived or it can be determined by the other methods. So if you put all these values, the value of V comes as 331.6 meter per second. Okay, and what is the standard value for the velocity of sound in air? That is 332 meter per second. So this value is very close to the experimentally determined value. So what we can say is that Laplace equation is very correct. So with the help of the Laplace formula, we can determine the velocity of sound in air. Okay. Now this was up to the determination of velocity of sound in the air medium. Now we know that sound travels in the another medium also. It travels in the liquid medium, it travels into the gaseous medium. So what we have to do if we want to find out the velocity of sound in the material medium, okay, material medium, that is the solid medium. So in order to determine the velocity of sound in solid medium or material medium, there was one scientist whose name was Kundts. Okay, so he devised some experimental arrangement, and that experimental arrangement is called as a Kundts tube. So with the help of Kundts tube, we can determine the velocity of sound in the material medium. So what this Kundts tube is actually, so just observe this particular diagram. Now this is a glass tube, okay, hollow glass tube. In this particular diagram, the hollow glass tube is shown, whose length is about 1 meter and whose diameter is about 5 to 10 centimeters. Okay, length is about 100 centimeters and diameter is about 5 to 10 centimeter. So this is a transparent hollow glass tube, just like a fluorescent tube which exists in our home. Okay, only thing is that that white color has to be removed, right? So whatever left, we can use it as a Kundts tube. Okay, now what is done? Now it is hollow. Okay, so both the ends are open initially. So what we have to do, at one end of the Kundts tube we have to fixed one cardboard. Okay, we have to fixed one cardboard A, and it is attached to a piston. Okay, it is attached to a piston. Now this particular block A is free to move along the length of the tube. It is free to move along the length of the tube. We can move this part A with the help of this piston. Okay, and another end of this glass tube is fitted with the another cardboard B. Okay, this cardboard is made up with the help of wood or the paper. Okay, so it is a small cardboard and it is attached to the rod BC. It is attached to the rod BC. This BC is the rod. Okay, and it is made with the material. It is made with the material at which we have to determine the velocity of sound waves. At which we have to determine the velocity of the sound wave. Now this is attached to this particular cardboard B. Okay, and in order that this rod BC should not fall down, it is supported at the position D. Okay, so at the position D there is one pivot. Okay, so this particular rod BC is supported at the position D. So this rod is resting at the D. Okay, this cannot be regarded as a slit. It should be regarded as one type of pivot. Okay, or one type of supporting edge. So this rod BC is supported at the position D. Okay, now what is to be done? Now before starting the experiment, okay, what we have to do, we have to remove this cardboard B and we have to distribute. Actually we have to dry this whole thing. Okay, we don't have to keep any liquid molecules over there. So we have to dry the complete tube and we have to distribute, or we have to scatter the lycopodium powder inside the tube. Lycopodium powder is a powder which is used in the carom board. Okay, so that has got particular significance over here. So we have to distribute that lycopodium powder inside the tube, and after that we have to insert this cardboard B and rod BC, and it should be supported at the position D. Right, now there is some fixed position of the piston A. Okay, it is fixed at some position, for example. Now what we have to do, we have to take a cloth. We have to take a cloth and we have to rub this particular rod BC. Now when we are rubbing the rod BC, what will happen? Longitudinal wave will be generated across the rod, right? You can imagine that if we have a rod of iron and if you just rub that particular rod, so you will hear some kind of sound. So why you will be hearing some kind of sound? Because after the rubbing there is a generation of sound waves inside the rod or on the surface of the rod, and that sound waves are giving me some kind of sound. Okay, so you have to rub this rod BC, and such that when you will rub the rod there will be the generation of longitudinal wave or the sound wave, but this rod is supported at position D. So if it is supported at position D, there will be the formation of node. There will be the formation of node at the position D. Because why node? Because since it is supported, we are touching at the position D. So all the particles at the position D will not be vibrating at all. and therefore such a position will be called as a node. So node will be formed at the center, that is at the position D, and obviously antinode will be formed at the positions B and C. So there should be the formation of node at the center and antinode at the position B and C, and you can easily measure the length of the rod BC, right? Whatever is the length of the rod, that will be now the distance between two antinodes, and distance between two antinodes is nothing but lambda by 2. So if lambda r is the wavelength of the sound wave on the rod, then this distance BC, that is denoted by LR. Okay, this distance BC, that is denoted by LR, or the length of the rod, will be equal to lambda r divided by 2, where lambda r divided by 2 is nothing but the distance between two antinodes. So such a pattern we will get across this particular rod, and that is invisible. Okay, so by assumptions only we have to say that this is nothing but the distance between two antinodes. Now what will be the effect of the formation of these antinodes inside this particular tube? So what will happen actually, once we have rubbed the rod and there is a formation of node at the D and antinodes at the B and C. So this antinode means at this particular position the particles will be vibrating with maximum amplitude, and if the particles are vibrating with maximum amplitude, so these vibrations will be transferred into this particular region between the A and B. Okay, so there will be the travel of sound waves from this position B towards the position A. So sound waves will be propagating inside the tube also. So sound wave will be propagating in the form of compression, rarefaction. So it will travel from B to A, and at the position A there is a piston. So sound wave will be reflected from the piston. So initially it is traveling from B to A, and then it will be reflected, and it will again go from A to B. Now there is one wave is moving from B to A, another wave is moving from A to B. So there will be the superposition, and these two waves are having the same wavelength, same frequency. Therefore whenever they will superimpose, they will form the standing wave. Okay, so standing wave pattern will be formed inside this tube. Now how we can recognize that there is a formation of standing wave? So what we have to do, we have to shift this piston, we have to move this piston to and fro such that we should get the loud sound. Why? Because whenever this piston is moved, okay, the length between these two A and B will be integral multiple of wavelength, half the wavelength will be integral multiple of half the wavelength, and at some point there will be the formation of resonance. At some point there will be the formation of resonance, and therefore all the particles will be vibrating with maximum amplitude. So if they are vibrating with maximum amplitude, so we will get the loud sound. Okay, so this is one signal by which we can say that there is a formation of resonance inside the tube, and another signal will be given by this lycopodium powder. Actually, you see, we have distributed the lycopodium powder. So suppose that at a particular position of the piston we are getting the resonance, it means that there is a formation of standing waves. So when there is a formation of standing wave, what will happen? At the ends A and B, there will be the formation of antinodes, because here there cannot be the formation of nodes, right? So there will be the formation of antinodes. So you can imagine that this is the antinode, and then there will be the stationary wave, okay, and there will be the formation of antinodes at the position B also. So you see that the lycopodium powder inside the glass tube will be distributed like this. Because of the formation of standing wave inside the tube, the lycopodium powder will be distributed like this. There will be the hips and this downfall. Now this position of hips is nothing but the position of node. Okay, remember that the lycopodium powder will be vibrating with maximum amplitude. But where it will vibrate with the maximum amplitude? Where the actual sound wave is forming the node. Okay, there the lycopodium powder will be distributed like this. Okay, you imagine that initially the lycopodium powder is distributed all over the tube. Okay, and there is a formation of standing wave over here. So wherever there is a formation of antinodes, the lycopodium powder will start from there, and wherever there is a formation of node, the lycopodium powder will have the peak over there, or will have the heap over there. Okay, so distribution of lycopodium powder will be like this. So this will be the position of the heaps will be the position of nodes of the sound wave inside this air medium or inside this glass medium. Okay, now this can be easily observed by the naked eyes, right? And we can measure the distance between two heaps. Okay, we can measure the distance between two heaps, and distance between two heaps is nothing but the distance between two nodes, and it is again lambda by 2. So if lambda a is the wavelength of the sound wave in the air medium, remember that lambda r is the wavelength of the sound wave in the material medium, and lambda a is the wavelength of the sound wave in the air medium. So if lambda a is the wavelength of sound in the air medium, so this distance between two nodes, okay, distance between two nodes will be LA, because distance is in the air now. So LA will be equal to lambda a divided by 2. So we have got two equations. One is LR equal to lambda r divided by 2, and LA equal to lambda a divided by 2. Okay, so LA equal to lambda a divided by 2. From this equation we get lambda a is equal to 2 times LA, and from this equation lambda r is equal to 2 times lambda r. Lambda r is equal to 2 times LR. Now if VA and VR are the velocities of sound in air and the rod, okay, whenever the sound wave is moving across the rod, let us consider that VR is the velocity of sound wave inside the rod, and when it is moving inside the glass tube, so inside the glass tube there is a air medium, so let us consider that VA is the velocity of sound wave in the air medium. So if these are the symbols, then we know that velocity is nothing but frequency multiplied by the wavelength. So VA is equal to n into lambda a, and VR is equal to n into lambda r. But lambda a and lambda r we have already found out. Lambda a is equal to 2 times LA, lambda r is equal to 2 times LR. So we get the equations like this, and if you divide these two equations, VR divided by VA, so it will be n into 2 times LR divided by n into 2 times LA. So 2 times n will get cancelled, LR divided by LA, and finally VR is equal to VA into LR divided by LA. Now what is LR? LR is the length of the rod. What is LA? LA is the distance between the two heaps of the lycopodium powder. And what is VA? VA is the velocity of sound in air. So this is also known to us. Its standard value is already known to us, VA. LR can be measured, LA also can be measured. So with all these measured value, we can determine velocity of sound in the rod or in the material medium, right? So this is the expression for the velocity of sound in the material medium or the rod medium. Okay, so in this way we can calculate the velocity of sound in any material medium. Okay, so next we will see in the next lecture.